have the time. Yeah. So, somehow in my setup, I can't see anyone, but I'm hoping everyone can you can see me, Shomindu, is it?
Yes, I can.
Yeah. See. Okay, great. So I'd like to welcome Professor Whitney Newey to the Delhi School virtually, unfortunately, but that's the way things are right now. He's made such seminal contributions over such a long period of time that I'm really not going to say anything about them. They've been ranging from non-parametrics to parametric work to statistical theory. I find this foray into machine learning especially welcome because these tools are getting so popular. And as we use them and find them useful, I think it's really important to know what the drawbacks are and how to use them properly. If judges, if the police, if everyone's making decisions based on machine learning, we better do it right. And so I think for the profession and for us, this is a really welcome new literature that Professor Newey is venturing into. So thank you so much, Professor Newey. Over to you.
Thank you for the invitation, a kind introduction as well. I'm happy to be here. I wish I was there. And don't we all in the days in which we live? Hopefully things will improve soon. This is work that I started, I started talking to Victor about this. He's been working on this a little longer than I have, but it turns out the work is quite related to things that I had done earlier. And you'll see that a little bit later, that there's some connections to the older thing. It's the older work in semi-parametrics in particular. And so it's exciting to be doing this. There's a lot of interesting work going on. And we're happy to be working together with others on this, and look forward to being helpful to the development of this. It provides a new way of allowing for very high dimensional models in econometrics and applied economics that's very promising. Even my colleague, Josh Angrist, has written a paper called Machine Labor. And it focuses on the very early work, what I'm going to talk about, but there's more recent work too that I think will also be helpful. So that reference won't be here, but you can look it up on his website or just Google it, and it gives some nice examples of applications in labor economics, and many more to come, I think. So this talk, let's see. Oops, sorry. This talk today, what I'm going to do is do an introduction, and then talk about some of the papers, mention some of the papers, and then today this talk is going to be building up to what we're going to do later. Okay, so we're really kind of building a foundation for what we're going to do later. We're going to talk about some basics of machine learning. We're going to talk about Lasso, some basic methods of machine learning. We're going to talk about Lasso, neural nets, and just a little bit about random forest. And those are just three of the basic methods people are using and what they're good for and why they're interesting. And then we'll turn to looking at trying to estimate economic things that are interesting using these methods, and talk about some challenges with that and how to overcome them. Okay, so many economic and causal parameters depend on first steps that are non-parametric or high dimensional. Regression slopes is one. You have many potential covariates that you want to control for possible emitted variable bias. Okay, so many potential covariates to control for possible emitted variable bias. Okay, And that's a very natural one, and that's the machine labor, Josh's machine labor paper. Talks about that, talks about a nice application where machine learning is quite helpful, actually. Another important example is average treatment effects, where there are many covariates potentially that you want to condition on to control for possible selection bias. And that's another important example. And we have worked on that and are continuing to work on that. And we'll talk about that in these lectures, actually, quite a bit. And then there are many other examples of policy effects of various kinds, average derivatives, and other things. And we will talk about some of these too. Now, machine learning, it provides a useful way to estimate high dimensional first steps. Okay, so that's the common feature of these things. They depend on non-parametric or high dimensional methods or things like regressions in particular, and that's what we're going to focus on is regressions. And they depend on high dimensional regressions. True for the regression slope where there are many covariates, there's many other variables around. It's going to be true for the average treatment effect too. And then all of these things, there's going to be in the background a high dimensional regression. And the thing that we're going to be interested in is something that depends on that. Okay. Something that depends on that. Now, what do we mean by machine learning? There are some methods that we're going to focus on and talk a little bit about. There's Lasso, there's Neuralness, and random forest is another one. Okay. In these lectures, we'll talk about Lasso, and we'll talk about it in a little bit of detail. We'll talk about neural nets, less detail. And even less detail for random forest because they're both neural nets and random forests are a lot more complicated. So we're going to kind of introduce some concepts around Lasso and focus on that as a method. The kind of approaches we're going to give to estimating economic objects of interest, though, won't depend on that. Actually, you can use any of these methods to do what we're going to do. And to estimate objects of interest, and we'll talk about that. Okay, these can be used to do regression with many covariates, estimate the average treatment effect, and estimate some of the other objects that we mentioned here: policy effects, average derivatives, and so forth. Okay. All right. So these lectures are based on 3 papers that are fairly recent. This is all pretty recent work. This paper on double debiased machine learning from the Econometrics journal, that's joint with Victor and 5 other authors. There's a paper that's just recently become forthcoming in Econometrics called Locally Robust Semi-Parametric Estimation. That's got a lot of the theory of this, the things we're going to be talking about. And then there's a paper with Victor and MIT grad student Rahul Singh called Automatic Debiased Machine Learning and Structural and Causal Effects. So that's going to be the focus of these notes and these lectures is going to be these 3 papers, and we're going to kind of build up. We're going to have the 3rd lecture will be primarily about this paper. Okay, and along the way, we'll kind of motivate what we're doing and then talk about this paper. And then this paper kind of is the theory that kind of underlies why this stuff works. And so we'll cite some results from that, but we're going to focus on really on the double machine learning paper and on this automatic debiased machine learning paper. Okay. There are more references. I didn't send a bibliography, but there are full references embedded in these slides, and we'll point them out as we go so that you can have access to them. Okay. Let's then apologies. Let's see. Let me just make sure I'm on the right page. Yes. Okay, so move the that thing down. Okay, so we're going to look first at this example 1, regression with many potential covariates. Okay, the notation here is going to be common throughout. There's a data observation that consists here of 3 things. There's an outcome variable y. There's a variable of interest d. That's going to denote a treatment dummy and later, but now just think of it as another variable, just a right-hand side variable in a regression that affects y, and z represents possible covariates. Okay, so we're going to start with this example here, regression with many potential covariates, and in that example, the data consists of the left-hand side variable, the outcome variable, the regressor of interest, and some covariates. Okay. And what we're interested in is the effect of d on y while controlling for or holding fixed z. So here's what that regression model is going to look like. We're going to have, the expectation of y given x. X is d and z. We'll say that it's equal a linear combination of d plus a sum from j equals 1 to some p bar of some coefficients beta j0 times variables that can depend on z. Okay, so this is just a regression specification. This is the variable of interest d. So the parameter of interest, we're going to denote that as theta naught all the way through. And then these are nuisance functions that are around. They're put in to avoid omitted variables bias, right? Standard regression motivation for putting in other regressors. Okay. Okay. Now they're going to be functions of z. They could be z's themselves, but this just is a little more general. Allow any function of z, and z can be infinite dimensional. So you can think of a sequence of z's, z1 through z infinity, if you will. They could also be nonlinear functions of z. That's possible. It's just a way to write, a lot of covariates is in terms of these BJs. Okay. Right. Excuse me. Right. Okay. So the parameter of interest here is this theta naught, which is the effect of d on the mean of y given x, y given d and z. So it's the effect of d on the mean of y holding z fixed. It's the usual. This has a causal interpretation under certain conditions, but from regression, what d is, right? I mean, what theta naught is. It's the coefficient of d in the regression where you have a lot of other covariates. Now this p bar is large here. You want to think of this as large, and in fact, we're really going to think of this as being infinity. It's simplest actually to think of it that way. This is just an infinite number of possible covariates you could include. Okay, and getting them all in eventually can be potentially important. P bar is the potential number of covariates, can be large. P bar equal infinity is allowed for. And P bar could also depend on the sample size, but we're not going to go there. We're not going to look at that type of specification. That's sometimes the early literature on high dimensional regression used that. P bar was the number of potential regressors, and P bar was large but not infinite. And it's the setting we're working in basically we're gonna think of this as infinitely large. Okay, this P bar is infinitely large, and this is a kind of a infinite sequence or series rather of functions. Now, of course, for this to be well defined, a lot of these beta J's will be small. And, you know, that's the kind of thing we're going to assume here. Okay. So it's a regression. You've got a variable of interest with its associated parameter. And you've got these other variables, BJs, with their associated coefficients. A lot of them are going to be small, so that this can be, you know, this has meaning, mathematical meaning. You know, it's going to, basically, this is going to be, you know, this is going to have finite mean square, finite second moment. Okay. Right, we focus on p-bar. That gets us away from the sparse specification where you let the specification of regression change with n, but it has all the same features of it as I'll talk about in a minute. Okay, a lot of the main features of it. Okay, let's see if I can move this. No, too far. Right, okay, so this parameter, theta naught, that we have here, you know, the coefficient in that regression can be thought of as depending on this regression. And that's the way we're going to think about it. And there are many important settings where X can be high dimensional, and we want to allow for that. A good example is estimating demand with many prices. That's a good thing to do. Lots of economic applications. Okay, where we want to allow X to be high dimensional, including covariates to control for possible omitted variable bias. You know, again, we're allowing for high dimensional X there. And I'm gonna not keep saying that. Presume that this audience understands the motivation for regression with high dimensional X. Okay, there are lots of examples, right? There are lots of examples. Okay, so next, what we're going to do is just assume that we're interested in high dimensional X and talk about methods that allow for that. Methods of doing regression when you have a lot of covariates, or just a lot of variables X in the regression. Okay, where we're headed is we're going to explain why and how machine learners have to be biased. Okay, it's in their nature, and they're going to have to build in some bias in order to have the possibility of having a lot of these X's in there included in the regression. Okay, and we're going to talk about how to overcome the bias for estimating this theta naught. Okay, and we'll give an empirical example. It's actually today, we're just going to do a Monte Carlo example, but we'll give empirical examples later. And I'm happy to pause for clarification. So I built in some blank slides here. I'm happy to pause.
Professor Newey, there's just a couple of things. One is that are there some basic books you would suggest? Is there a basic book you would suggest before they actually get to this on machine learning, just so that they get the basic ideas? And then there's beta JZ. Does that have to be a monotonic function? And I think not, right? But I think
no,
it could be anything. Yeah. And yeah, that's the substantive questions here.
Okay, great. So there is a book that's very good, a very good introduction by, I think at just 1 second. I'm going to pull it off my bookshelf. This is a good text. Okay, it's called The Elements of Statistical Learning. The Elements of Statistical Learning. It's by Hasty, Tibshirani, and Friedman. And this is a great introduction to machine learning, actually. The Elements of Statistical Learning. Sorry, I'll get it on the screen here. Okay.
Yeah, great.
Yeah. and it's a good introduction. Okay. You also can pick it up from, let's see, the debiased machine learning paper, the double machine learning paper has some material in it. And Victor has done a couple of survey things that has some of this material in it too. And there's also a textbook that we're working on that will have some of it in it, just a basic introduction to things like Lasso and also to neural nets and some other things. So that'll be available pretty shortly, I think. So that's available too. Okay.
Great, thank you.
Yeah. And then, right, and good question about the DJs. No, they're just meant to represent any functions of Z, any functions of Z. You know, a simple specification would just to say BJ is ZJ, and then ZJ goes from Z1 up to Z infinity. And that's a simple specification that you could do here. Okay, so machine learning is a collection of modern adaptive statistical learning methods for estimating regression functions and other statistical objects. We're going to focus on regression here. Other things it's used for are classification. It's used for classification, which is great. It's actually used for dynamic discrete choice. There's a whole field called reinforcement learning that it's used for. That's kind of an economic summary of what they're doing, but they're solving dynamic optimization problems using machine learning, reinforcement learning, and there's other methods too. That book, The Elements of Statistical Learning, has a great survey of those and an introduction to a lot of those. Now, these methods, what they do is they exploit structured parsimony restrictions. And one of these is approximate sparsity. We'll talk a little bit about that today. Together with various forms of regularization and model selection to enable high quality out of sample predictions in spite of being high dimensional. Okay. Key methods include Lasso, neural nets, and random forests, and we're going to talk about Lasso a bit. So that's the simplest, that's the easiest connection to this literature, I think, for people who know some econometrics, because it looks like regression. It's very closely related to least squares, and you were just going to do it a little differently. And so I think it's a good way to get access to the literature and to the tools, actually, to begin to use machine learning or to think about it. And so the goal, all right, so those are some of the key methods. And then the goal of these lectures is to help you understand how to deploy them to infer economic and causal parameters that depend on regression functions. Okay, so we're going to focus on regressions, conditional means, basically, and we will, I'm going to introduce Lasso enough so you know what to do. You could use it. Neural nets a little less, so they're quite a bit more complicated. But we're going to kind of sketch what those look like, and there's software available for those and for Lasso for that matter. Sorry. Still figuring out sorry. And there's software available for doing this. And we'll just sketch out a little bit about that so you have an entry point. Okay. And then we're going to look at examples. We're going to look at the regression coefficient with many covariates, and we're going to look at the average treatment effect and how you use machine learning to estimate that. And there are many other examples, and what we're going to give the third lecture is a whole framework that covers a lot of things. It includes regression, includes the average treatment effect, average treatment on the treated, and other interesting objects that we'll mention, and will allow you to do automatic debiased machine learning, to use machine learning methods and then automatically get a way to apply them to a problem that you might have, the estimated parameter that you might be interested in. Okay, so that's where we're going, is to get to that point. Okay, to right here, help you understand how to deploy these methods to infer economic and causal parameters that depend on a regression function, or regression functions for that matter. Okay. All right. So let's talk about Lasso for a little bit. Okay. So Lasso basically is designed for an infinite dimensional regression. That's the way to think about it. And the way it was originally worked on or set up was that the regression function is a finite linear combination of a lot of things, a lot of potential things. You have an infinite number, a lot of regressors available to you in the data, and the regression you're interested in estimating is a linear combination of a lot of them. We're just going to go all the way to infinity, okay, and just say that the regression function is a linear combination of this sequence of functions of the regressors. Okay, you can think of this as a representation of a nonlinear function in terms of approximating functions or Fourier series in particular. Okay, so the focus is on, yes, you can think of this as approximating a nonlinear function by an infinite, you can think of this as a nonlinear function where these are Fourier series. Turns out for full power series and for splines, it doesn't quite work, right? Okay, so we're going to leave that aside from this point on, but I did want to mention that that's one of the caveats of this setup, the Lasso setup. You're kind of limited on, how you get a full approximation of a nonlinear function. It's a little bit limited, okay? Most of the high dimensional literature up till now has not focused on that. The idea has been, more appropriately interpreted as a high dimensional regression where there's just a lot of covariates that you could potentially put in, okay? With maybe that are distinct regressors with some nonlinear functions included, okay? Now throughout, we'll have data, and for now, we're combining the Z and D that we had before into X. Those are combined, those are just regressors. We have data, and we're going to assume throughout that the data are independently and identically distributed. So we're not going to worry about clustering for these talks. We're not going to really focus on clustering or an autocorrelation. We're just going to take look at the IID case. Now, this is important for Lasso. It's more than just a normalization. And so we're going to introduce it right away as we talk about Lasso. The regressors need to have the feature that they have the same scale. And you'll see why in just a minute. So the way this is done in practice is when you go to plug in your regressors into a Lasso regression, this is generally done automatically, not always, so you need to check it. But what is done with Lasso is they should take the BJ of X, the functions, the regressors here, and they subtract out their sample mean and they divide by their sample standard deviation. And that normalizes them so that they all have the same scale, okay? And it's important. It's actually important. Otherwise, it turns out, unless you do that, it turns out Lasso doesn't have the same benefits as a high dimensional method. So it's important to do that. Okay, so that's just kind of just mention that along the way. Okay. Oops. Let's go down. Okay. Okay, so here's Lasso. Right, normalizing this normalization so that BJ has sample variance 1 or sample second normal 1 is actually essential for good performance of Lasso in high dimensional settings. Okay, so now let B of X denote the first P elements, first P possible regressors. Okay, the Lasso learner or regression estimator is you just take the sample mean of Y, so Y bar is the sample mean, and you add to it this linear combination of the normalized regressors, the ones that have had their sample mean subtracted off and divided by their sample standard deviations, where the coefficients for these non-constant regressors are gotten by minimizing the sum of squared residuals, right? Subtracting Y bar off Y because you subtracted the mean off here. So you partialed out the constant. And you minimize the sum of squared residuals plus a penalty. Okay. And this penalty is 2 times lambda. Lambda is the degree of the penalty times the sum from J equals 1 to P of the absolute values of the beta J's. Okay, so this second term there, that's an absolute value penalty. And this problem is very nicely behaved, it turns out. It's not least squares, you're not just doing least squares, so it's not as simple as least squares, but it's objective function here is convex in this beta, and fast computation is available in MATLAB and R. They are great programs now to do Lasso. Okay, and easily available in standard software. I think in Stata, actually, there's a Stata has a Lasso routine. One of my co-authors is using it for some of our joint work that we're working on. And we're estimating taxable income as a function of some budget set regressors. We're using Lasso to estimate how they depend on the budget set regressors, and he's using Lasso and Stata, actually. So it's readily available. Okay, so that's what it looks like. It's the least.
Professor Newey, there's a question
Sure.
on what performance actually means. So what do you mean when you say it's essential for good performance? And so what I have a question, which is that this penalty that you have, the beta J's, are the estimated parameters, is it, for when you use the first P regressors?
Yes, it is when
Could
you
you
use the
explain?
first. Yes, absolutely. Yeah. So you have to pick P. The thing is that P can be very large. Okay, in principle, the theory allows for P to be much larger than the sample size, actually. So we couldn't do that if we were running least squares, right? You can't have more regressors than the sample size, right? That doesn't make any sense. You just get a perfect fit. But because of this regularization here, that allows P to be very big. And that's what makes this high dimensional, actually. Is because you're penalizing, you can put in a lot of potential regressors. And you can put a lot of, you don't put them in, but you can have a lot of potential regressors. And so that's what makes this different than just running regression on some, approximating functions like linear, squares, cubes, and so on, is you can have a lot of potential regressors.
So is one of the questions going to be the what the value of P should be? And does this sort of, is this, when you're sampling, it's always this trade-off between sample size and precision and so on. But the penalty, if you could provide some intuition for penalty term,
Absolutely.
or you could do that later. That would be fine.
We will, absolutely, we will. The penalty is what controls that. The fact that you're selecting, you can literally, the theory says that you can grow at some power of n, the sample size. It could go, anyway, you can grow, the number of regressors can grow really fast. So the theory is agnostic about p. Actually, it is not agnostic about lambda. Okay, it's the penalty. One of the neat things about Lasso is actually by picking lambda, you can guarantee optimal choice of which regressors are included. Okay, so it turns out there's a rate that you can specify for lambda, which guarantees that you have an optimal convergence rate for this thing, for what thing the gamma hat of x. And so that's a really neat feature of this, and we'll come to that actually. The theory and actually the practice is silent about p. It is true that good performance. What we mean by that is good out of sample mean squared error. Okay, so that was the other question. What do we mean by good performance? It means good out of sample mean squared error, that it produces good predictions out of sample. That's what we mean by good performance. Okay, and then so let's just step back a minute. Okay. Good performance means good out of sample mean squared error predictions. Predictions that have sum squared prediction errors that are pretty good. Okay, and p, the theory is silent about p. The finite sample performance can depend on it though, and so we don't really. The idea is you just pick p large. And throw in a lot of potential functions and then let the data tell you which ones are important to treat this penalty.
So there's another question related to that, which is the distinction between p and p bar. So is p bar just the maximum and p is what you're picking?
Exactly. Think p infinity, p bar infinity, and p is something you pick in applications that's large, but less than infinity, obviously. But it's large. Yeah.
Great, thank you.
Very good. Okay. Now, what this does, what this does is it puts a penalization on least squares, so it's going to shrink the coefficients towards zero. Right? It's instead of getting least squares coefficients, you're going to get something that is you're penalizing the size of them. Okay, and that's shrinking the coefficients towards zero. So shrinks the Lasso slope coefficients towards zero. Okay. Okay. We're going to talk about that in a minute. Okay. So what's going on here is that this you want a good fit. This is this is the fitting part. You're trying to fit the function, fit this linear combination of these basis functions to the y's, right? By minimizing least squares. But I'm going to say, I'm going to put on this penalty. What that does, it turns out, is it shrinks the Lasso coefficients towards zero. And by putting this penalty, it's a kind of regularization that helps control the variance of the estimator when p is much bigger than the sample size. That's really what's going on. Okay, so it's regularization that helps control the variance of this. Obviously, if you put in n, if you set p equals n and you tried least squares, you just get y back. You get perfect predictions of y. That's not useful. But here, by putting in this penalty, what you can do is you can control that variance. Okay, and shrink the coefficients towards zero, and do it in such a way actually that gives good mean squared error for out of sample predictions. Okay, and we'll talk about how to do that in just a second. Okay, but okay, so this has two features. One feature is you allow for a lot of possible regressors, many more than the sample size potentially. But you're going to shrink their coefficients towards zero using this penalty. And what that's going to do is it's going to set things so that the important variables in here in terms of prediction, the ones that help reduce this, right? The betas, having the betas in there that help reduce this, those are going to be important in this part. Okay, and so they're going to end up being they're going to end up showing up bigger in here, right? So this, notice here that you penalize every beta the same. Okay, and so the ones that are important here, that has the least squares criterion gets lowered by choosing those betas different than zero, okay, a lot. On the other hand, the ones that aren't important here, it doesn't get lowered a lot. And what's going to happen is actually those betas are going to be driven to zero. Okay, so there's shrinkage. There's also selection going on with this. Okay, so let me go to the next page. Yeah, sorry about that. Yep. This is okay, so this next page is an example. But that's the intuition of how this is working. This next page is just going to be an example. The intuition of how this is working is, the betas that help fit the Ys, or the Bs, that help fit the Ys, those will be important in helping make this small, the least squares criterion small. And so they're, in spite of the fact that you have this absolute value penalty, they'll still show up. But the other betas, the ones that aren't important, they're going to be driven to zero actually here. And in fact, a feature of Lasso is that a lot of coefficients are zero. It shrinks them towards zero, but actually makes them equal to zero. And that's because of this absolute value penalty. It comes in, it comes in sharply towards zero, and so there's a lot of cost locally as you move away from zero. So it tends to drive coefficients towards zero. There are good pictures that I'm in the literature on this, in that book. The Elements of Statistical Learning, there's good pictures that explain this. Okay, so that's the intuition here. So the marvelous thing about this, the thing that we like and love, and what that has captured my imagination and a lot of other people, is that you can allow for a lot of B's. P can be larger than the sample size. So why is that interesting? Well, think about, trying to specify covariates where you have a lot of interactions. Suppose, there's just too many to do all possible interactions, but you can put a lot of interactions between different covariates in, and then let Lasso tell you which ones are important, okay, in predicting why. And so that's the potential here. That's why machine learning is not the old non-parametrics. I've sometimes gotten this reaction from very good, smart people, but it's not, because you're not just putting in powers of, X's here in some sequence, you're putting a lot of stuff in. Powers of X, interactions between different X's, and powers of different X's interactions, and lots of potential covariates, and then the data is going to tell you which ones are important. Okay, and so it's not the old non-parametrics, it's not the old series estimates, it's something different. All right, and you see it here, it's because of the tight link to regression, linear regression, you can see it. here. You get this penalty that provides the regularization that allows you to potentially to have many, a high dimensional specification where there are a lot of potential regressors. And then a lot of them are also going to have coefficients set to 0. Now, let me just say that we started by saying that we said these methods exploit structured parsimony restrictions, such as approximate sparsity, where many regression coefficients are small. Okay, so you don't get, there's no free lunch, right? We know that, right? And so you still need something going on here to let this work. And for Lasso, it's approximate sparsity. It's not that a lot of coefficients are small or 0. You don't need that. Sparsity, you may have heard, maybe you even heard this isn't interesting because it requires sparsity. It doesn't require sparsity, but for this to work well, there's got to be a lot of coefficients that are small. The cool thing is you don't need to know which ones they are. Okay, you don't have to know which interactions are important. In principle and in practice, Lasso can help tell you that. Yeah, Lasso can help tell you that. Okay. All right. So let me just give an example of this. And this is, I'm going to, at the risk of, okay. So yeah, let me just look at the picture here. Okay. So what this is you're putting in a lot of functions, okay, to try and approximate what's here is education and here's the wage. Okay, very simple setup. And it turns out that if you look at the mean education, and this is from the CPS, I don't remember what year, but if you look at the mean wage for education level, it moves around a lot, right? And so if I try to do a series estimate here, where I just put in powers of the years, right? I'm not going to do very well. I'd have to get very high number of powers to try and track this form. But if I include powers, and I also include some piecewise linear pieces, splines, then actually you get a super fit pretty quickly with, you put in a lot of functions, you put in the powers, but then you put in some piecewise splines, things that are just linear over a segment, and you actually get a pretty good fit. Much better than you get with the just putting in the powers, right? So this is, like a third the size in terms of the mean squared error, right? A third the size. And the point of this is, well, Lasso allows you to do that. You can put in a lot of functions and then let the data tell you which ones are important. Okay. And that you can't do that if you just adding powers or adding something like that. This allows you to select among different kinds of approximations as well. Okay. So this is the conventional. What you got is a 0.12 for the L2 mean squared error. This is root mean squared error, and Lasso is a lot less. And then if you do something called post Lasso, it's even better. Okay, and what post Lasso is going to be is that's what you get when you use Lasso to select which ones are non-zero, and then do least squares using those that have non-zero coefficients. Okay, we'll mention that. Okay, so that's just an example, but it's just meant to illustrate, why this isn't the old non-parametrics, and why you can benefit a lot from using these kind of high-dimensional things with penalization and trying to get something that fits well. Okay, I'm going to go ahead and go on. Is that okay? Any questions? I was going to pause here, but I'm a little bit, I should probably go on. Any questions?
Yeah, please go ahead.
Okay, go ahead.
Oh,
Okay.
there's one question from Deepthi. Deepthi, do you want to just unmute and ask it? You'll probably ask it better than I.
Sure.
No.
Okay.
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 Could you perhaps just tell us whether lambda is chosen by you before the exercise, or lambda is a constant that is lambda a choice variable that you
Lambda is a
choose before you
choice.
start?
Lambda is a choice, and most frequently it's chosen by cross validation, and I'll give that in just a minute. What we mean by that. If you run it in Stata, you get to choose a cross validation way to choose it, or there's another way to choose it. Cross validation is thought to be set lambda a little too small potentially. But it's now known, Victor has, with Dennis Chekverikov and Zhipeng Guo, they have a paper in the Annals of Statistics, forthcoming in the Annals of Statistics, that actually show that cross-validation is optimal for in terms of mean squared error. But it's thought in practice that maybe it sets lambda too small. So we'll talk, I'll get to that actually momentarily. Okay, so let me first plot a, let me just look at the chat for a minute. Do you first plot a graph before you decide on the B's? Probably a good idea. Yep, that can help you. When you have a simple one. Of course, the virtue of this is it allows for high dimensions, so there it's harder to plot, but that's a good idea. If you're just trying to set it fit a function, sure. Let me just look back here. Does y need to be normalized too? No, no worries. Let's see. Why is the normalization important? Okay, the reason the normalization is important is because you're putting the same absolute value on each of the betas. So if you have different scales, then you're penalizing different coefficients differently, different variables differently, and that's not a good thing, right? So that's why you normalize the B's. So because the betas are just there, right? They're treated the same. Every beta is treated the same in the penalty. And so that's why you normalize the scale of the regressors. Okay. What else? Let's see. Yep, predictive performance. Yep. Okay, so that's good. Let me go down and okay. All right. So let me go ahead then. Okay. Okay, so right. So here's right. Don't want to miss this page. Lasso sets many or most of the coefficients to be equal to 0. We mentioned that. Lasso is implicitly doing model selection. The SS in Lasso stands for shrinkage and selection. That's what the SS stands for. Post Lasso is OLS on the dictionary of functions with non-zero Lasso coefficients. This does not shrink coefficients towards 0, but it does select which ones to use in the regression. And it tends to be less biased. So that post Lasso is a useful thing to know about. Often lambda is chosen by cross validation. Okay, so this is how you would describe that is the following. Divide the data into L about equal sized groups. L's typically about 5, sometimes 10. I think the default in Stata is 10 actually. And then let little l index these groups. Let gamma hat L lambda x be the Lasso estimator for all observations not in the Lth group, IL. And then you choose lambda to minimize this out of sample predictions, right? So this is the prediction error. You're predicting yi using xi and all the other observations, but the ith. Well, everything that's not in the Lth group here, okay? So it's a kind of cross-validation or, forecasting yi using gamma hat, not estimated using yi, okay? And you do that over a grid of possible lambda values, and lambda is chosen to minimize the sum of squares of prediction errors for out of sample forecasts. and then use this lambda hat in the calculation of beta hat. MATLAB and R and Stata will do this for you, and typically L's 5 or 10, something like that. Okay? Okay, so let me just, okay, so on the theory, I'm just going to give you, don't worry about the assumptions. I'll just mention them briefly. I just want to get to the bottom line here. So under some assumptions, you actually get by an optimal mean square rate for the gamma hat. And so that's the cool thing. And it's optimal in a wider sense than the normal non-parametrics. It's optimal when you don't know which functions are important. Okay, so it's a kind of, you know, we would normally think of approximating by some functions, you know, like series estimation, good non-parametric method. You put in powers of X, for example, or you put in splines, and then you can get a good rate for that. You get actually the same rate for this up to a log n term, when you don't know which functions are important. That one, you know which functions are important. You put those in the first, and you get a good rate. This one, you get a good rate without knowing which ones are important. And again, that's the virtue of this, right? You can throw in a lot of functions, a lot of potentially important functions, and still get a good rate. Now, the rate does depend on this sparse approximation rate. And so what this says, I'm just going to say it and try and say it in words rather than read through the equations, is what this says is you put in a lot of these functions, P of them, can be many times the sample size. Somewhere among all of them, all of those P functions, there's a few S that deliver an approximation rate. And that's what this is. So this B bar has a lot of zeros in it. It says that somewhere among them where you don't know where it is, you don't know where this is, somewhere among them are some important functions which approximate the regression function in mean square at rate S to the minus C. That's exactly the kind of thing we do with series estimates. Only we know which ones they are. You put in the leading terms and you get an S to the minus C. Here you can put in a lot of them and you don't know which ones are important. And you're still saying you get an S to the minus C. Okay, so this is like series estimation where you don't know which functions are important. Okay, and then under some conditions, there's this sparse eigenvalue condition that controls the singularity of this matrix. It's, you know, you can show that it's true under some conditions. You get this mean square rate, which is actually the same or very close to the usual mean squared rate, except for this little bit of penalty. Okay, and actually, the way this is written is not the optimal one. The optimal one just has log P here. This is a theorem that's in one of our papers, and it's just not quite as good as the best theorems. I'll just say here that this rate here, this rate of convergence that you get here, is the optimal one up to log P. The one that you would get was a series estimate if you knew which ones are important. So that's the cool thing here. You get the same rate of estimation in estimating this function, not knowing which functions are important. Okay, as you do when you know which ones are important up to a log P term. So it actually doesn't affect the rate as a function of n at all. If P grows, you know, some power of n, you still just get a log n term here. Okay, and so in terms of the rate of estimation of the unknown function, that's the nice thing with Lasso, is you get a rate that's just as good as you knew if you knew which functions were important, up to a log n. Okay. So we do not have to know which elements of this basis are the important ones. Lasso picks those for us. You can make P very large to help guarantee you have the best dictionary functions. Okay. Remarkably, Lasso convergence rate is only slower by log P. So that's why I put this in. Not the conditions are interesting, but just the conclusion is interesting as a theory, econometrics or statistical theory thing. Okay, so that's the kind of thing that's captured, as we know, machine learning works very well in some settings. Okay, so neural nets. Let's talk about neural nets. So that's Lasso. Any questions about that? Let me just pause for a minute. Let me check the chat. Okay, question, as in normal econometric techniques of linear regression, how can we identify significant covariance in a machine learning technique? They're a little hard to, actually, it's hard to pick out which covariates are important. And oftentimes we don't care. We just need them to control. And that's what this is for. You just need the right ones to get the controls right. So that's what, that's what you don't, Lasso's not good for picking out which ones are important. There's a lot of noise in which ones are exactly zero versus which ones are a little close to zero. But you don't care if all you care about is a good control for all the covariates together. That's fine. If you're adding a penalty to the objective function, then why is the normalization important? It's because it penalizes the beta the same. All of them, right? We talked about that. So, okay. Okay, so I'm gonna speed up a little here. Okay, so neural nets. Okay, so I'm just gonna give a very brief discussion of what this looks like. Okay, it's a different technique. This is the one, though, that does amazing things for prediction out of sample in very high dimensional settings, right? Things like voice recognition, lots of other things. A lot of those are based on neural nets. We don't actually know as much about them. The theory that I just gave for Lasso is only in its infancy for neural nets, actually. There's some interesting results. I'll give you a couple of references. You can go look at the papers. There are actually a couple of really great papers now that good introduction to this. But these things perform amazing in terms of out of sample prediction in very high dimensional settings. So I wanted to at least give a brief introduction to what they are. Right, so nonlinear regression model with many parameters that's used to estimate the conditional mean. Remarkably good out of sample predictions. And what it does is it uses as regressors the same monotonic transformation of different linear combinations of regressors, where the regressors may themselves be monotonic transformations of linear combinations. So what it is, it's kind of a nested set of regressors where the different regressors in the nest are themselves linear combinations of, is a monotonic function of a linear combination of regressors. That's what it is. This is notation that's meant to describe that. The nonlinear regression, you start with some regressors, okay? You take linear combinations and monotonic functions of them, and you form new regressors. Then you take linear combinations of monotonic functions of them and you form those all the way up to here. And then you go back and do nonlinear least squares to estimate all the parameters in those linear combinations. Okay. Now that's computationally very difficult. So let me just look at the next bottom here. Right, but this is what they look like. See, here's the monotonic function of a linear combination of some regressors. These V's themselves have this form at a lower level, starting down here. That's what a neural net is, okay? This is a correct mathematical description of what they are. but intuitively, you're just taking linear combinations of regressors. They have these coefficients on them, and then you're going to estimate those coefficients, and then just a huge nonlinear least squares problem. It sounds impossible, right? It's actually not. They've developed algorithms that help these things perform amazing in doing out of sample predictions. So this is actually where some of the amazing performance you hear about machine learning is. Okay, so here's just a single. Okay, so they depend on this nonlinear function. The most common and theoretically interesting one is just a max of 0 and u. And a single layer neural net approximates the expectation of y given x by constant, of course, and then linear combinations of this nonlinear function. It depends on a linear combination, set of linear combination coefficients, linear combination coefficients, okay? So that's what a neural net looks like, a single layer neural net. That's what it looks like. Multi-layers, these x's themselves aren't the original regressors. They depend on linear combinations of functions of a linear, this function, activation function of a linear combination. And and then this thing has just amazing performance. Okay, when you do out of sample prediction. Let's see. Okay, so that's the one level, and how the heck, how do you do nonlinear least squares on this? Okay, we'll come to that in just a second. You actually, what you do, I'll come to that in just a second. Okay. Deep neural nets have more than one level, where these x's are themselves of this form. Okay, and then you do least squares to minimize the least squares objective function by some algorithm. Okay, all right, now what algorithm? The algorithms for doing least squares to estimate neural nets often involve drawing these alphas randomly as starting values and then just doing gradient descent for the OLS objective function without iterating to convergence. Repeating that for different starting values and then averaging the results across different starting values. Not iterating to convergence is one form that regularization takes. They sometimes penalize them explicitly with doing ridge type penalties or sum of squares of coefficients or other things. This is more of an art than Lasso. These aren't convex objective functions, no way. Very non-convex objective functions, but they've been hugely successful in out of sample predictions in very high dimensional settings. There's very recent theory given mean square rates at which the mean squared error of gamma hat minus gamma naught, the population mean squared error converges to 0. They depend on the depth and width of the network and how many derivatives exist. And there are some structured sparsity features to these things, actually. Turns out here's one very nice paper, Schmidt-Heber, 2020, just a little over a year ago in the Annals of Statistics. Very nice paper, showed that actually you can estimate functions that are compositions. Not surprisingly, you're sort of taking linear combinations and linear combinations and so on. So functions that are compositions, you can estimate better with this than you can with a series estimator. You can show that you can get faster rates with this. And that's what he did. Schmidt-Heber did. And then there's a nice paper also on Econometrics with giving rates by Farrell, Leanne, and Israel. Okay. So that's all I'm going to say about neural nets. Unless, let me check the chat here. Let's see.
Professor Newey, I have a question.
Yes.
This is Rohini. So is there much distribution theory for these estimators, or is it just a matter of prediction that
it's a matter of prediction primarily. Great question. And no, there's not much prediction theory, but there's not much estimation theory. There is theory for things that you plug them into. That's where we're going, and that's the next lecture, actually. There is theory for things that you plug them into. You can get nice distributions for those. So somebody asked, can neural nets be used for estimating causal effects as opposed to out-of-sample predictions? Absolutely. Yeah,
I
we're going to
see.
talk about how to do that. So once you get to the economic object you're interested in by applying some formula the right way to these things, yes, there's theory for those. You can get standard errors for those. Yeah, that's straightforward.
So do you feel as a broad approach that actually this problem that we always have of have you omitted covariates, do you feel this machine learning algorithm sort of somehow get us over that as a first step?
It helps, absolutely, it does, because you can put in lots of things and get a good forecast, and that's enough for that's basically enough for getting rid of the effect of covariates, actually, right? You just need it to predict. Think of parceling out, right? What do we want to do? We want to regress Y on the covariates. We want to regress X on the covariates. And so that's all about a prediction problem.
Right. But then it just depends on whether your sample is, this out of prediction questions, out of sample predictions become important. I mean, if you're applying this, the advantage with a model is that if you really believe this is what the world looks like, then you can just take that coefficient and then apply it anywhere you want, right? But
that's true. That's true. So it does depend on just really that all you care about is the one coefficient.
Right. Yeah. Another broader question is you've done a lot of work on unobserved heterogeneity in statistical models in general. And how do you think this work relates to that? There seems to be some connection because, you're putting in a bunch of stuff and you don't really know what the model is. But would you articulate a closer connection between these two? Do you think there is one?
There is. I think, so a lot of those models of unobserved heterogeneity in the end depend on a lot of regressors. Like an example is panel data. If you think about one way to control for unobserved heterogeneity in panel data is to let the unobserved variables depend on X's from all time periods. And so there's a lot of hope there that machine learning might be able to regularize that in the right way. Actually, and something that I'm thinking about and others are thinking about is how to use it to kind of allow for all of those X's from all time periods to enter the right way, but do it in such a way that it doesn't, cause too much of a problem in terms of.
That's very interesting. Thank you. Thank you.
Yeah. So yes, absolutely. Absolutely. Okay. So all right. So anyway, so that's that one. Sorry, I'm moving on, but that's, okay, so random forest is another method. I'm going to skip it. Okay, it's a great one. It works well. It's complicated. That you've got software to do it. Okay, you've got software to do it, and it got some of the best. It's when you run it in horse races to do prediction out of sample, it really works pretty well in a lot of settings. The theory for that is even more recent, and here's one paper. And on doing the theory. And even this is a bit of a special case because it's binary regressors. Okay. How about comparing? Okay. In some Monte Carlo comparisons, Lasso works well for linear regression. When there's an infinite number of regressors. Sorry, oops, let me move down. Sorry, back. Where did I go? I'm going the wrong way. Sorry about that. Random forest. Okay, we talked about that. Comparing them, Lasso works well for linear regression models. That if it's actually linear and it's a set of regressors, covariates, it tends to work quite well. Neural nets may give better out-of-sample fits for the important nonlinearities. Generally, they do. It does. That way of controlling for nonlinearities, that function of a linear combination of things, sort of index models, That tends to work pretty well, controlling for nonlinearities. Random forest gives really good out-of-sample forecasts and some examples based on real economic data sets. Susan Athey, just check out anything that has random forests in her on her website and find good material. Okay, an application to estimating slope coefficients and things like the ATE, they all tend to get pretty similar answers, and we're going to see an example of that next time. Okay, so next, what we're going to do is talk about how to estimate these parameters of interest. So we got these great, as Rohini was saying so well, we got these great out-of-sample forecast things. You know, how do we use them to estimate parameters we might be interested in economics, like a coefficient, a theta, in a regression, or an average treatment effect? Okay, and so now we're going to talk about that. The most obvious thing is to plug in a machine learner into a formula that takes the regression and gives you the object you're interested in. The average treatment effect is like that. There's a formula for it in terms of the regression, right? Jim Hahn's paper and other papers about that. Okay. And lots of things. Actually, the coefficient can be written like that as well. We'll talk about that later a little bit. Sort of odd, you know, we'll talk about that. Go ahead, you had a question?
No, I didn't.
Oh, okay, that's all right. That's all right. So it turns out the obvious approach doesn't work. Okay, the obvious approach doesn't work. And the reason is because, oops, sorry. The plug-in method, where you just plug in a machine learner into a formula of interest, it's very biased. Quite generally, not for every case, not for every machine learner, but a lot of them. And the bias just comes because of the regularization and the model selection. Okay, you think about it, you know, with Lasso, you're shrinking all these coefficients towards zero. You're shrinking the coefficients in all the variables, and that introduces a lot of bias. And Lasso tends to have lots of biases. When you take a Lasso estimate and you plug it into some formula, you know, like an average treatment effect formula, you tend to get very biased estimates. Okay, and it's just associated with getting good predictions. You know, in high dimensional settings, you know, you have to regularize to get good predictions. If you really have a high dimensional specification, you just can't put all those variables in. The variance blows up. So what do? Well, you do something to introduce some bias, and the regularization equals bias. You know, you're just trying to control the variance some way. You're trying to introduce a little bit of bias to control the variance. And so that bias passes through. In all these formulas, it tends to pass through to the parameter of interest and makes the estimator very biased. Okay, and I'm going to give an example of that to estimating the coefficient in a regression. Okay, so that's what this example is. Okay, so I'm gonna just do this. It's a little bit of a funny way to go about doing that. Let me just say that right up front, but it illustrates what can happen when you just plug in a formula. Okay, so when you just plug a machine learner into a formula. So here's a formula that theta naught satisfies. If you look at you take y and you subtract off d theta naught, and then you multiply by the residual from regressing d on z, that has mean zero at the true parameter. Okay, so this is a kind of moment function you could do GMM for, where you plug in a machine learner here, right? You're going to do, you know, the part of parceling out where you partial out the regressor, right? You're going to take the residual from regressing d on z using some machine learner. You're going to plug it in here, plug in that machine learning residual here, and then solve for theta tilde by setting the product of this machine learning residual times y minus di equals 0. here's what happens. Okay, when you do that. Sorry, next, the other way. Oops, it's there. Sorry. Oh, one more, two more. No, sorry about that. It's there. Where'd it go? Sorry. What happened? Just a minute. It seems to have gotten stuck. 1 second. Yeah, well, there it is. There's the graph. Okay. Okay, so the thing on the left, the thing on the right, that looks okay. The thing on the left plots the distribution of this estimator that we just did. When the thing it's supposed to be is the red curve. Okay, plots the density of this estimator when the thing it's supposed to be is the red curve. So if you think about the parameter being 0 down here, that's what the 0 is right in the middle. And think about a t-test and a t-test of the parameter being 0. You know, how often would you be rejecting the t-test? Way more than 5%, right? Because it's shifted way to the right. And so with Lasso, and this is actually with random forest, so you can get it with random forest too. You get similar things with Lasso, you just get huge biases. Okay, if you just take them.
Could you clarify the difference between the two graphs, Professor?
Yes. This is what happens when you plug in the formula. This is what happens when you debias the right way. Okay.
Okay.
So we're gonna introduce a way of debiasing that gets rid of this, and this is what it is. And for the I'll just say for the regression, we're nearly out of time, right? Well, we got 8 minutes. For the regression, it's partially out. Okay, and there's something like partially it out you can do more generally to get rid of this bias, and that's what we're going to focus on after today.
Yeah, I have a slightly tangential question, so I don't know.
That's okay. Fine.
You know, a long time ago, people said, "Look, if you have too many covariates, you can't do regression. So you know, compress them in some way." And so you had all this factor analysis and principal components, and that was just a way of minimizing, combining these variables. Now, it seems to me that this has some of that flavor, but the big advantage is that you're taking the Y into account, because all of that didn't really tell you which. You were just sort of lowering the variance and you were combining them, but you really didn't have any sense of what is causally important. And so do you feel it's related in that sense, but it takes the machine learning takes the Y into account?
Yes, this takes the Y into account because, or takes the D into account here, but this absolutely takes the Y into account. I mean, if you think about Lasso regressing on the D, right, the regressor you're interested in, and on all of these other variables, right, what you're getting is how it fits Y, right?
Right.
Yes, absolutely. But yeah, you're not just trying to figure out which one's important among the X's, you're just trying to figure out what helps predict Y.
And you're going to talk later about the optimal choice of P?
Yes.
Okay.
Yeah, a little bit. Yeah. Okay. Of what? The
initial set. So the penalty term is going to
actually just put it all in. That's not true. Actually.
Okay.
I would try what you do. What you do is you try different specifications and see if your estimates change much. That's what you do, and that's not that different. But they can be large specifications, right? That's kind of you can put a lot of interactions in, for example, right? And try, anyway. So, hundreds and hundreds of regressors, right? That's the idea.
Even in your initial set P, when you're choosing the.
Yeah.
Yes. Okay.
Well, I would honestly, what I would do is I would try a few and then try more and stop when, as I do that, you tend to, your estimate settles down. actually.
And there's
That's
no
what I
fear that you're data mining because you weren't pretending to be causal in the first place.
No, you weren't pretending to be causal. Yeah, the causal thing comes later. You're just trying to fit the thing.
Yeah.
So,
Okay. Thank you so much.
absolutely. No. Yeah, no, I would, well, though, let me come back to that next time. Let me finish this and I'll come back to that next time. That's a great question. I want to think about it before tomorrow, actually. So,
okay. If there yeah, so I'm sure many of you have questions, and there's a breakout session. I mean, for our 10:15, Shomendu, is that right for us? Let's
15 IST.
10:15 IST, which is tomorrow morning, Professor Newey. And is there anything else? Because we have 5 minutes. So if there are any other questions that people would like to ask, if you can just put them in chat and I'll just call on you and unmute you if needed.
oh, that's a great question. Why feature selection is needed in forest regression? I don't know. It's probably beyond my capacity even to talk much about that. So it's you have to select in what order you kind of divide up the data, right? And in the end, what you do with random forests is you do that in a bunch of different ways, and then you combine them randomly, and that seems to work amazing, actually. But I don't know what feature selection is needed in forest regression. They have ways of doing it, but I am not that. I could not even attempt to explain, and it would take too long too. Sorry about that. Can you please give 3 examples when the sparsity assumption does not hold? Yes. Okay. An example is when all the coefficients are the same size. You know, if no coefficients are more important than another, then the sparsity assumption doesn't hold. Okay, and so that's what you're really counting on for the approximate sparsity to get this good properties, is that the important features are somewhat concentrated. You're absolutely depending on that for Lasso, right? Any practical recommendations on selecting P for Lasso? Good question. I think trying some different values of P is a good idea. And I have found in applications and estimating structural economic parameters that P matters, actually. What it tends to do is it tends to raise the variance a bit. So would you de-emphasize Lasso for choosing regressors rather than controlling for covariates? Yes, it's not very good for choosing covariates, actually. There's a lot of noise in which ones that, when you get down where the coefficients are quite small, there's a lot of noise in which ones are actually 0. So if you're actually selecting covariates, yeah, if you needed to do that for some reason, I'm sort of against that. For reasons we'll talk about a little bit. Yeah. Let's see. Selecting P for Lasso, I would just try a few different sets, a large number, a medium number, and a smaller number. And what you tend to find is that the variance goes up. You know, after a while, after putting on quite a few, the variance tends to go up without affecting the estimates very much. Okay, so we're out of time.
Thank you so much. Thank you, Professor Newey. So we'll see you when you wake up in the morning. Okay, and the parallels, thank you so much. The parallel sessions, everyone else, start at 9:45. So hope to see you there. Thank you so much. Bye-bye.
Bye-bye.